question that popped to your mind during the break about barrier methods? It's pretty simple as a concept, right? Okay. So now I want to show you how you can get around these problems, and it's just a bunch of transformations on this thing here. And the beauty is that it will reconnect to a very nice interpretation of what is happening in this context. So let's work a bit on that. So again, now you have the NLP, the KKT conditions that would normally be attached to this guy. So with this problematic corner-like manifold. If you go for the barrier formulation, so again, constraints in the cost using the barrier function. And the KKT conditions you have then here, simply the stationarity of the cost function. So that's going to be this thing here with possible sign that is problematic. Should check that. But it reads like this. Okay. What we will work a little bit on these terms here, and something will happen. So let's look at these terms here. And what we will do is replace this stuff here, so the h-1s times tau, by a new variable. Let's call it new I, for example. So one for each constraint. And in some sense, it's kind of clear why we want to do that. If you think about it, when you approach a constraint, this hi minus 1 is going to 0, and the tau, so yeah, the hi minus 1 is going to infinity, hi is going to 0, and the tau is going to 0. So in your KKT condition, you have essentially something becoming very small and something becoming very high. And when you multiply them, it's supposed to come again to something of normal values. But in the computer, it's not cool to have to deal with large and small numbers multiplying each other, right? That's how you get problems. So you would bypass this issue by just saying, by renaming this product something different, and then you will work with this thing in the computer instead. So replace this problematic product by something else. So what you can do then, you rewrite this guy. So now this minus tau hi minus 1 is my new I, and I still need to specify in the computer that this guy should match. So essentially I'm rewriting this equality here in this form here. So just multiplying by hi on both sides, I get this, right? So I could replace solving these conditions in the computer by solving these two conditions together, right? And when I do that, I don't really have this problem of something very small and something very large. I have something small, something small. Okay, in principle, I can live with that. Okay, so I jumped from here to there. Next, so I'm just collecting these things together, essentially. I can rewrite this sum of new I nabla hi as a scalar product, actually. So it becomes, it's not obvious maybe, but I can write it as nabla h new, essentially. So these new i's, I would collect them in a vector and rewrite this as a scalar product. Whoops. And I can just shift the tau on that side of this equality, and I still have to enforce these guys. So h negative, and the new has to be positive because the hi is negative, right? So okay with that. So just this small transformation of these conditions. Now compare these conditions. So it's coming from the barrier problem to these conditions here. And you essentially see that they are suspiciously the same, right? So I have essentially the same equation here than this one. I have also the product between these variables and the hi, this variable and the hi. One difference is that I add plus tau here, and then instead of saying that they have to be greater or equal or smaller or equal, I replace with strict inequalities. But apart from that, basically I'm talking about the same algebraic conditions as the original KKTs of the problem. Now if you take Newton steps on this guy, things are nicely behaved. I mean, I don't have this very small, very large products. Everything is fairly simple in here. Okay, let's try to push this a little bit further to give some meat on this similarity. So again, so these conditions, when you work with the KKT conditions, gives you a corner like this. It's annoying to work with this when you do Newton. What we saw is that these barrier methods, you can reformulate them by essentially solving these conditions here instead of just finding the gradients of the cost function with the barrier being 0. Okay, so this thing here, what would it look like in this picture here? I don't know if you see where this is going. It looks like a parabola, right? Essentially, that's the manifold of this equation. So essentially, when you do a barrier method plus a bit of reformulation, what you're doing is you're transforming this corner here into something hyperbolic, which is smooth. Newton could work with that because it would understand how to go from that side to that side. There's no corner left here. And of course, what happens if tau is decreased is that you make this hyperbola look more and more like the corner. But you always keep a bit of round here so that you can go through this point using Newton. Okay? So essentially, and when you do that, you're actually talking about primal dual interior point method. And essentially what's happening here is that you replace this nasty condition by something smoothed by just adding this small perturbation. And you convert this corner into a roundish thing. And as tau is decreased, your equations look more and more like this one, or the solution looks more and more like this one. And it's the same story as for the barrier method, obviously. So the distance between the solution you get from these conditions and the solution you get from the original KKT conditions is in the order of tau. So make tau small, this will be small. And it's kind of obvious from the equation, but this nu is actually a proxy for the mu, right? So this is a close approximation of the dual variables. And so this order also holds for this guy. So the nus that solve these equations would come tau close to the mu's that you would normally have if you generally solve the original KKT conditions. Does that make sense? Yeah? And again, you can understand the interior point thingy because the solutions you get out of these equations, you will always maintain H inside the feasible domain. You will never achieve 0. It will always be at somewhat inside the feasible domain, so slightly negative, and the nus will always be slightly positive. But it's again in the order of tau, so you can make them as close as you want to the true solution. So when you call IP-opt, it's basically solving these kind of conditions. And the multipliers you get are not the mu's, they are the nus, and they are as close as you want from the true ones. And same for the w's. Okay? Okay, then we can go one step further and discuss how you actually deploy Newton when you use these primal dual interior point KKT conditions. So the KKT conditions, now I can throw back my equality constraints in the game. It doesn't change anything of what I said. The equality constraints, that's always the easy part to handle in the solver in principle. So these are the original KKT conditions. To get the IP ones, I will just disturb by this tau, and I will ask these guys to remain inside the feasible domains. I can summarize my equations that way, just replacing this stuff. That's always the gradient of the Lagrange function. So I need to solve these guys using Newton. and somehow I will have to find a way to keep that valid all the time. And of course, what you would do is take Newton steps on these equations. Now I have a set of smooth equations with this plus tau. So I can essentially label these guys, let's say R of tau, R for residual, for example. So it's a function of the primal dual variables. And this function will depend on tau, obviously. You could see tau as a parameter in these equations that we will adjust eventually. And you need to take your Newton steps on the W, lambda, mu's using these equations, and somehow we'll have to handle this. Okay, so Newton direction or Newton steps, always the same story. So you take the Jacobian of your equations times the step plus the equations must be 0. That gives you a primal dual Newton step, and you could take that step on your primal dual variables, maybe some step size, so a t between 0 and 1 to make sure that things converge, and that would let you find the w's and lambdas solving these equations. Now, how do we handle this? It's actually fairly simple. You start with w and mu such that this holds, right? You start with w's that satisfy the inequality constraints and the mu's positive. And then you would always adjust the length of your Newton steps such that you stay on the right side of these inequalities. So you have a w and mu that satisfy these guys, and then you get the delta w, delta mu from the Newton step, and then you adjust the t, the step size, such that you don't go over the 0, essentially. And that's it. That's how you handle this problem. Okay, mathematically it's simple. In practice it's a little bit nasty, mostly because of this guy here. That's easy to check. If I give you mu and delta mu, it would not be very hard to find a t that keeps everything with the right sign. But this h plus t delta w is going through this function h, and that function maybe is not simple. Why not? You could think, for example, if you're doing a single shooting and w would be your inputs, and the constraints to evaluate them, you would have to simulate everything. So the relationship between the variables and h having the right side or right sign can be a bit tricky. Yeah, that's a bit of a problem when we do that, and that actually motivates an extra feature in these methods that is state of the art nowadays. Yeah, also you need to start with this holding, so you need your initial guess w to satisfy the inequality constraints, and that's also quite tricky. That will be on your shoulders to find that. That can be difficult. So to solve that problem, people use typically a slack reformulation of the primal during interior point conditions. And again, it's a super stupid trick, but that works very well. So get back to these conditions, and you need to ensure that all the time. That's a bit tricky. So what people do is this. Introduce a new variable. It's almost the same story always in optimization, just introduce more variables to solve your problems. So S for slack, call it minus S equals H. And that will be a constraint in the NLP solver. So you would add this line in your conditions, right? So essentially you're just saying S must be like H at the solution. And then you replace this product, you replace the H by S, and you replace this condition by minus S less than 0, right? So it's just writing this equality and replacing H by S in all the equations. Can just change the signs here. It does not make any difference. And now everything is solved because it's very easy now to pick an initial guess for S such that this holds. I mean, just pick it positive, that's all. And you can even pick your mu's and S, the initial guess, such that this holds when you start. So you can start your mu and s on the hyperbola. You don't need h to be to have the right signs on the initial guess. This constraint may start infeasible, and Newton will fix that. So it will basically bring s close to 0 possibly, and force h to come to meet s. So it will enforce the inequalities on h in the end, but as you proceed, you may have infeasible h on the way. So you satisfy the constraints in the end. And then finding the step size, that's very easy. You have your s and mu's, that's your current guess. You get the Newton step, delta s, delta mu, and you just check what is the largest t I can use such that this holds, and pick that as a starting point for a line search. So everything becomes easy. You just introduce some more variables in the problem. And again, when you run something like IPOpt, it will be doing that for you. You don't see it, but it would have these like variables inside. Okay with that? Simple, yeah? Okay. Okay, so now we have this complete formulation. So again, all the equations with a slight reformulation. That will be the KKT conditions without the relaxation. Now the relaxation is just the addition of this tau on the condition. So that's what we work with. And now you will apply Newton on all these equalities. Sorry. So that's the Newton system that you will solve. Newton direction, as always, given by this thing. And now it's interesting. If you look at what this matrix looks like, this Jacobian, so it's del R, del all the variables, W, lambda, mu, s. It has a very specific structure that you would see in many papers. So you see here that would be look like the KKT matrix we had without inequality constraints. That's not surprising. All this stuff is there to handle the inequality constraints. And now you have the gradient of your inequality constraints. You have an identity matrix here. You have a matrix made of your s's on the diagonal and your mu's on the diagonal. And it will always have this structure. And that's the Hessian of your Lagrange function. And you can probably guess, if you remember, so this H and nabla G from optimal control problems, they are basically banded. The H would be banded. These are diagonal matrices. This is a diagonal matrix. So this guy has a very strange structure, but it's very sparse as usual. So it's also fairly easy to handle in the computer. And there are techniques to do efficient linear algebra on this specific structure here. Okay? No question? Okay. Yeah. All right. Well, we can play a bit with that now. One question I should still talk about now is essentially, if I want to get an accurate solution, I need to solve these conditions for tau very small, right? That's how I get very close to the true solution. And tau would be really in the order of 10 to the minus 5, 6, 8, 10, depending on what accuracy you want. So I resolved my corner problem, but kind of only partially. I mean, if I'm using something that is very, very sharp here, it's still a bit tough for Newton to go through. So Newton does not like very strong curvature. So if tau is very, very small, it will still be something that looks close to a corner. So it will be possible to go through with Newton, but it would probably take many, many iterations to navigate a very sharp corner like this. So we want to solve these conditions for tau very small, but it's not easy to handle these equations if tau is very small. So how do we solve this problem? Yeah, just a reminder, Newton does not like strong nonlinearities, so we need to handle that somehow differently. And maybe one way of understanding what will happen there is you have to think that when I'm talking about going through the corner using Newton, you need to do that if, for example, your initial guess is on the wrong side. So imagine, let's say that you suppose that this constraint I with these multipliers and these slack variables, let's imagine you thought it would be active at the solution. So you you would start your solution with an active inequality constraint and a mu that is positive. But it turns out that this at the solution, this constraint should be inactive. So Newton will want to move this point from this side to that side. So you have to go through a corner when you make a wrong guess about constraints being active or inactive, right? So when you have to deactivate constraints from the initial guess to the solution, that's when you go through the corner. Otherwise, you may actually navigate one of the branches and all is fine. If you are on the right branches, you don't need to see this corner. The key idea that all solvers do to handle this thing again is you start iterating with a large tau, so you make a very smooth corner. If you have to go through it, it's no problem. It's gonna be very nice and gentle. And as your iteration, or as Newton converges to r becoming small, you will decrease tau, make the corner sharper, and hopefully by the time the corner becomes very sharp, you are already on the correct side of your branches, and you don't need to bother about this corner anymore. Does it make sense? Yeah. So you start with a large tau, you solve your problem. Hopefully Newton will figure out on which side it should be, and then the corner becomes very sharp, but Newton may be playing around here, for example, so it does not care about this thing here. Okay, so that's a prototype pseudocode for a primal derivative point solver. You, for example, set your tau at 1. Why not mu and s at 1 as well, so that the complementary slackness conditions are already satisfied. You need a guess for the primal dual variables, the w lambda, and you would keep solving things until the tau is small enough. So essentially, it should be at par with your tolerance in the solver. And then you could do this essentially. You take this tau, you solve your primal dual KKT conditions for this tau, push it to 0, and then reduce your tau a little bit and solve again and solve again and solve again, right? And by the time tau is meeting the tolerance, essentially you have solved the problem. And so this, what we expect is that this will always be fairly easy to solve because you start with a large tau, and then Newton has figured out on which side it wants to be in these branches, and then so by the time you get to small taus, everything will work out fine. Yeah, I can show you that on a simple example. I'll reuse it a few times. So that's the QCQP actually. So you have a quadratic cost W minus W0, and it wants to bring me down here. You see the minimum of the level curves, but I want my W to be inside some ellipsoid-like thingy. So this red thing. So I don't want to leave that that's potato. Okay. The first thing we could discuss in this picture here. So you can imagine that for each tau that you can throw inside your conditions, you will have a different solution. So W lambda mu s, they will change as tau changes. Does that make sense? Yeah. And this path in the primal dual variables that satisfy the KKT conditions for different values of tau is called the central path in the interpoint method. So you can imagine you take tau going from 1 to 0, and you solve these conditions for each of these values of taus, and you display in your primal and dual domain, and you have S here. You display all these solutions you get from starting at tau is 1, up here and up here, and I solve for different values of tau this problem, the KKT conditions, and I get a path that of course goes possibly to the constraints for tau very small. You see that? Yeah. So you see that for tau large, the primal variables start deep inside the feasible domain. That's expected. You can imagine that in some sense the barrier is very, very wide when you do that. So you have to be deep inside. And as you reduce tau, the solution will be down here. Obviously, it wants to go to this point and it's blocked here. So as tau is reduced, the solution will navigate all the way to the constraint. And same here. This point corresponds to a hyperbola that is very, very wide. And as tau decreases, you get to this hyperbola that is very, very, very close to the corner. And that's the end point of this path. So you go from here to here. And what's going to happen if you deploy an algorithm like this is essentially you will go down the central path. So if you start with tau is 1 and converge this, you would converge to that point. And each time you reduce tau, you're talking about moving to a point down this path, all the way down to the solution. Right? So essentially, all these algorithms, they try to follow a path inside your primal dual space. Okay, so we can try that, really this algorithm. So let's initiate everything like up here and here. So it's very wrong initial guess, completely outside the feasible domain. Here in my mu-s space, I'm actually on the wrong side in some sense of my branches. Kind of trying to make hitting, well actually it's on 1, 1, so it's on the hyperbola. So it has to select between going here and there. It has to end up down there. So I can take a few Newton steps with tau is 1. I will nail that point here and nail that point here. So I'm basically hitting the entrance of the central path. Okay? So that's for tau is 1. Then I reduce the tau a little bit and take a few Newton steps. So that brings me here, right? And on this path, it brings me here. So now the hyperbola is, is moving. The hyperbola was here. Now it's coming here. And I keep reducing my tau. And each time I reduce my tau, I'll be brought down the central path a little bit. It's always hitting for this hyperbola crossing the path. And here it's tau is 10 to the minus 3 more or less. And I'm really in the neighborhood of the solution. Okay with that? Yeah.
Earlier you said that hopefully tau will be on the right side of the corner.
Yeah.
Will it always be, or is it?
In theory, no. In practice, yes.
Okay.
Yeah, you can put it that way. So actually you see that here. So essentially here the entire central path is more or less on the right side.
Yeah.
So it actually already here figures out that it seems that we are going for an active constraint. And it's indeed staying on that side. So it never goes through the corner. It's actually kind of floating around it, but by the time the corner becomes really sharp, it's actually already on the right side. So it's not really going through it.
Is this with a very kind manifold, just a circle?
Say it again.
Isn't this a very kind manifold?
Yeah, this constraint here.
Mm-hmm.
Yeah, it's actually a nice problem. It's actually convex and everything. Yeah.
Will it be more difficult to land on the right side with one of the problems you showed us in the first lecture, with where you had an intersection?
Yeah, it could be. I'll actually show you, if I have time today, some more difficult examples. Probably not. Next time, maybe, with non-convex constraints and so on. But so maybe one interesting thing is IPOP does that, for example. If it realizes that, oh, it looks like I have to go through the corner again, it just increases tau again. So the tau that you have in IPOpt, it's not only going down. If things go a bit wrong, it would kind of bump it up a little bit for a while and come down again, possibly.
But doesn't the pressure to go in that direction disappear?
The pressure of...
So the solution was when you reduced tau, the solution moved to the wrong side of the...
Yeah.
And when you increase tau again, won't you...
disturb that?
No, but yeah, go back to where you're...
Yeah,
to the wrong side.
possibly, but what happens in practice is typically if Newton picks the wrong side and realizes that it has to go through the corner again, it's usually because other variables in the problem are kind of moving on their own and have an impact on what you're doing on that side. So essentially it's like, oh, I thought that I was on the right side, but these variables are now turning the problem around and I'm not right here. So okay, let's relax tau a little bit again. I moved too quickly down. And you let these guys converge a bit more, decide what they want to do, and then go back again. So it's not going back to the same place as before. It's like, oh, I kind of took a shortcut. Let's come back and let everything settle properly and then move again. Yeah. Okay. So now, yeah. Okay. So that works. Solvers actually don't do that. They do something actually a lot more aggressive. And the problem here is, there's not really a problem, but for example here, you're taking many iterations to nail that point, but you're not interested in that point actually. You want to go down here. So actually, if you look at here, like the first Newton step is actually bringing you already very close to the central path that you want to follow. Same story here, huh? First Newton step brings you here. You are already on the central path. So all these iterations that you're taking to get to the entrance of the central path and these iterations here, they are actually useless work because there's no interest in going to this point. You will anyway go down this path. So what interior point method do instead is they would typically take a Newton step and then check how good this R tau is. And if it's good enough, then they will reduce it already. So you don't converge, just check that your R tau is reducing according to some norm that it's not easy to specify that. And try to update your tau as aggressively as you can. And that basically saves iterations. So you can imagine I'm doing the same exercise, but now I'll update my tau aggressively. And so I take one step, second step, and now this condition will be okay. So I reduce my tau already. So I was here, I'm like, okay, for me it's good enough, divide tau by 10. So move the goalpost and essentially the tau reduced will basically drag my Newton down the central path. And you just keep reducing as often as possible your tau. And then you will converge to your point much more fast, or much faster than if you converged all the time, right? And so these algorithms are essentially doing path following on this central path, trying to basically pull Newton forward or pull the Newton down the central path by always updating tau quite aggressively. That also explains why you may want to have to move it back up sometimes. If you did that too aggressively, you realize things are going a bit wrong. Okay, let's backtrack a little bit. Okay with that? Okay, so then I can give you basically a pseudocode of primal state-of-the-art primal dual entry point solver. So you build all the matrices you need, compute a Newton direction. So you have this primal dual interior point KKT matrix. You need to compute your step sizes such that these guys are always on the right side of the signs. And if you wonder how you do that, a classic way is to say that the new S that you will pick cannot, so you want to kind of always restrict how far it can go. So you make it larger or equal to S times an epsilon, where epsilon is small enough. So you kind of, if it wants to go for S equals to 0, you don't allow it to decrease faster than this kind of linear rate, essentially. So that gives you a Tmax. Then you may still want to backtrack a bit from that, so still do a line search to make sure that the R will be reducing, and then take a Newton step. And if you meet some condition like R is small enough, update your tau and keep going. So write this down in your computer. You will have a working interior point method essentially. There are some subtleties. For example, how you want to assess what you mean by R tau small enough to update the tau. There are some very smart ways of doing that, essentially measuring the distance to the central path. People use Merotra predictor. That's essentially saying when I will update my tau, how will the solution W lambda mu s change, and try to make a prediction of how it will change. That's kind of speeding up the procedure. And yeah, these adaptations, they are not frozen. Typically, they are more like adaptive and making smart updates on the taus. But yeah, there's a lot of development behind these small details. But the yeah, backbone of the code is essentially that. Okay. Yeah. Okay, you can make some examples. Yeah, that's actually optimal control. That would be MPC-like stuff. I would have an ODE given by F. Here I would write an Euler integrator. Why not? Some imposed initial conditions. I have some quadratic penalty, so I want my states to meet some reference. I have some bounds on my states and inputs, and then I throw in some non-convex inequality constraint in the problem. So what I'm talking about here is that it's a simple plane dynamic doing something like moving left and right. It's a very stupid system, but it's nonlinear and not completely trivial. So you would have x and y, that's the position of the plane, and the forward velocity that you can control. You have a heading that you fix by banking, and you have a roll rate and acceleration. And so what I want to do is fly along a path and avoid this region here. That's this non-convex constraint. So you can imagine that you have like a dangerous point here and you want to fly around it. I just want to show you a little bit what this interior point methods would do with this kind of problems and this kind of constraints. So here I'm solving for so all these KKT conditions, I solve them for tau is 1, so that's a fairly relaxed barrier, and I show you the norm of the residual, so all these KKT conditions that you get behind the problem. And here you see the interior point effect, which kind of becomes an exterior point thingy here. So you want to stay away from this zone. We solve it for a large tau. What happens is that the trajectory will basically avoid it by a big margin. That's the barrier effect that pushes you away. And here the solver is focusing on reducing R, so it's not updating tau yet. So it's reducing it until it's happy enough. And then now you have a reduction of tau, and that allows you to come closer to your constraint. And now you have the R reducing again, a new update of tau. And now you see, even though you have non-zero tau, you are like in practice essentially on the constraint, so touching your domain. And quite quickly you don't see any change really in the solution, so you should stop here actually with your iterations. Yeah, well, if you run that in an MPC fashion, it would actually look like this, right? Where are we? Yeah, I guess we should stop now. I don't have much left on this, but I guess I'll take it next time. Okay? Yeah.